All right. Good morning, everybody. Happy Wednesday. So I guess in the area where I live, there could be some type of internet outage sometime between 7:30 a.m. and 3:30 p.m. So I'm not sure if it's going to affect today's class, but we'll see. So let's see how this actually goes. So anyway, so for I guess some announcements, I guess I don't have the assignment 8 up just yet, but I will have it up soon by the end of this week for sure. It'll involve priority queues, min and max heap. It won't be really a tough one, so I probably don't have to even spend time talking about it in class because it won't be too hard to understand. Nothing too complicated. It'll be pretty straightforward what you have to actually do, or at least more or less. So I mean, I guess I could talk a little bit about it next week, but it shouldn't really be anything that's super complicated, really. So we'll have that, and I'll probably give us our graph theory program sometime next week as well. I'll give out an assignment on graph theory, so we have the rest of the semester to work on that. So that'll be probably a more interesting assignment than the heap one. So anyway, that's sort of like the announcement for right now, I guess. Nothing else to really say for right now. So anyway, guess I'll go ahead now, just sort of continue from last time's content and see how class goes. Hopefully there's no outage during class today. So, sorry, screen share. Let's just resume from last time's class. Okay, so we last time we're going over graph theory, sort of algorithm, and or graph theory representation, how to sort of take a graph and how to store it into memory, sparse graphs, dense graphs. So we kind of began talking about depth first search, which is really a very simple graph sort of traversal algorithm. So it's not really a search, although a search, it could be used for search, I suppose. But it's really just a traversal algorithm. All we do is when we reach a node, and then we just pick a neighbor to traverse to. So it's like, think of every node as a fork in the road. We have multiple sort of edges, and with a fork in the road, to quote Yogi Berra, if there's a fork in the road, take it, which means just pick an edge. And you go as far as possible as you can go until you can't go any further and you back up. So I'll first go over the code aspect of it, and I'll also kind of give a more layman's terms of how you can sort of think of depth first search. So anyway, for now we have the following four sort of components for depth first search: our adjacency list, our current node, our ID, so the node we're currently on, our visited array, and our predecessors. Okay, so let's first draw our graph. So I may have to kind of zoom out a little bit here. So I first draw my graph out. I'm trying to think how I can do this on one note. I guess I could just move this down a little bit to say make room for my graph. So I can then, I think I'll make a graph first, then I'll finish up this this code here. So one of the benefits of OneNote, I can go ahead and just do this very easily. So I'll write the code in a little bit. I want to first just give us an example graph. I'll also give you an idea of how you want to actually create adjacency matrix, or sorry, adjacency list out of our graph. So I'll go over that as well. Let's first go over and create our graph. So make just an example graph. So let's go ahead and just let's add a few nodes. Just make a relatively large enough graph where you have a good example where you can cover depth first search nicely. Let's see. Okay, I think it's a good number. I'm going to use numbers to represent node IDs. So we'll have, this will be node 0, node 1, node 2, 6, and 7. So you have 8 nodes in this graph. Then I'll draw arrows, but I guess I'll use this sort of method of making an arrow because this looks way nicer. I mean, you know, we're not cavemen SpongeBob, we have technology, right, Patrick? And of course, when that episode of SpongeBob happened, of course, he had to like, we knew it wasn't happening as soon as he said that. So, but I'm using technology this time. See, I'm using actual this structure. So this will make it look nicer. I'm going to add some more edges here. So let's try this. Let's try, and let's add some more edges. Um, this. This is a kind of completely random, so there's not a pre-planned graph, but really, I mean, this is going to work on any graph that first search. You don't really need to actually have such a, plan over here. So let's see. So I'll try this. Let me try this. Let's see. I think that works. Um, yeah, I think we can go ahead and go with that. I think that's a good enough graph. Okay. So this will be our graph we're given, and I'm going to go over sort of an idea of how we actually can create adjacency lists out of this graph. So the first thing we'll do is we're going to, from whenever we have to read a graph from input, we typically will be given the size of the graph or how many elements we're going to have, or have all of our vertices listed out. So we have vertices 0 through 7, so 8 vertices in total. So we're going to just create our adjacency list. We're going to have a size 8, how should we say, a size 8 array. So I'm going to use red to do this. Let's see, so 1, 6, 7, 8. So we'd actually create this array. So I'm going to first write the code here. So let me just put it, I guess I'll put it here for a second. So you would actually have the following. We would have node star star. And of course, you'd allocate this by saying adj list equals new node star. And we'll assume we have a variable called vertices, which is going to have how many vertices you're going to have in this graph. So this is going to basically create this structure. So I'm going to go ahead and say adj list, oops, spell, and it'll go over here just like that. And then we'll have our indices for this array. Oh, made it too large. Okay, fine. I'll just redraw this then. So it's fine. Very simple fix. Then I'll put the array brackets over here too, sure, just to kind of, just like that. Okay, so first have this set up, and then of course, let's do this kind of quicker. So I'm not going to use technology, just using old-fashioned writing this out, but it's going to be an array of pointers basically. So each of these will, so far, they're going to be set to either to null. I guess setting to null was a good idea originally, but anyway, um, we have that structure just like that. So, for example, in our file, we would have each edge would be in one line. So you'd have, let's say, for example, in our file, we'd have one line, which would have a 0 space 1, which says that we have an edge from 0 to 1. So, for example, if I read in one line 0, 1, then I would go ahead and go to adjacency list, index 0 equals new node. What that would do is it would just basically allocate a node. Just like this. May have to make this a little bit larger because I may have to, it's going to be a little bit complicated to draw this out. So I think I have to maybe have to redraw this to make it a bit larger. So that way it'll be easier to kind of fit this whole thing here. So I apologize. I'm going to go ahead and sort of redraw this because I want to make it a bigger table, or bigger, or a little bit longer, because that way it'll be easier to trace out that first search. So let's do one more time. So just pause for a second. I'm just going to just do this really quickly here. I won't even put array brackets this time, then I'll just do it like this anyway. Um, so 1, 2, 7. That might work a little better. So then I'm going to have a little more space in between these. So let's see. So we need 7 lines. Seven. I think that works a little better. So it has a little more space between them. So I'll go ahead and I'll just use just won't put brackets this time. I'll just sort of just use numbers like that. It's going to represent our indices of this. So the first thing we'll do is we're going to just allocate a node to that. Shape stuff right there. That. Okay. And then all we're going to do is we're going to set ADJ list index 0 arrow. Let me see, what was the actual field we had here? ID. Okay, sure. ID equals 1. We're going to set 1 to this. And then we're going to set ADJ list 0 link equal to null. Just like that. So if we want to go ahead and add another neighbor, so for example, here we have 0 goes to 3, then, well, I could do a tail insert into that linked list, or I can do a head insert. So I'm going to, get this all in chronological order, or I can sorted order, but to add another sort of neighbor into this list, it's actually more efficient to do a head insert instead, because we don't want to have to maintain a tail pointer for each of these nodes. So a better approach would be to use a head insert, which is a much more faster runtime, because a tail insert with no tail pointer requires you to traverse the entire linked list until you hit the end and insert to the very end like that, which could take a long time. So a head insert is a better idea. So I'm going to just erase this amount of space here, but of course this isn't in recording, so of course you can just rewatch this or you can jot these down. But I'm going to erase this right now so I can make a little room here to insert a different node into this, just to give you an idea of how you actually would build this adjacency list. But of course, this is actually kind of like the bare bones way of doing this. Of course, for assignment 9, you're going to have to actually use a vertex class or use the edge iterator class, of course. So it's going to kind of mask all of this pointer stuff within the class, but it's going to be this idea, but it'll make it probably even a little easier because I'll go over the examples of how to construct it using that approach I will use. So we're going to use obviously class and vertex and iterator within it just to make it more fun. But anyway, so if we wanted to go ahead and add 3 into 0's list, well, of course, in our file, we would have a line that would contain 0 space 3, telling us that we have an edge from 0 to 3. So then once again, I'd first create a temporary pointer equals new node. So what happened, I'll put this over here for a second just so you can kind of visualize it. But then I'll go ahead and I'll construct the rest of this really quick afterwards. I want to at least go over just kind of an idea of how to manage this structure. It's not too bad, but of course linked lists always cause issues for undergrads. It is maybe new for many of us, which is, I guess, makes sense. Now set temp what's the actual ID? So temp ID equals to 3. So I should have put temp this 3. And then temp link. So I want to set this to the front. So 1 is going to be the head node at the moment. I want to set 3 in front of 1. So I'm going to then say temp link equals ADJ list index 0. Now, of course, these would be not literals. This would be a variable. So every line has a source and destination node that tells you the edge. Edge goes from 0 to 3. So these would be both variables most likely. This is going to basically set temps link point to that. And then I want to go ahead and set AD. So this is the next line after this. I'll set ADJ list 0 equals 10. We'll update this pointer point over here. So as you can see now, 3 has been inserted before 1. So 0 has 2 nodes in that linked list, 3 and 1. So end result is going to basically just be the following. So when I'll redraw this, it'll just be 3, 1. This would be the result. Now, I guess for the rest of these, I'll keep it chronological just because I'll keep it sort of in sorted order. But it doesn't really matter what order they're in, because here, ADJ list 0, as long as we have 3 and 1, the two neighbors of 0 is 1 and 3, it doesn't matter what order they're in, as long as they're both there. So a head insert is a better idea because it does save time. But of course, you could do a tail insert. It won't cause any problems, but you have to traverse the entire list and then insert to the end, or you have to maintain a tail pointer for each of these linked lists, which is also not really convenient. So head insert is the way to go. So I guess I'll just erase, I think I'll keep that there because it's not going to hurt anybody by having that code there in red. But let's go ahead and just insert the rest of these into this linked list. So that's kind of the idea. So hopefully I gave you an idea of how to maintain this. So on traverse a list, I guess I'll go over this in a second so we can do that first search. But anyway, let's go ahead and do the rest of these. So 1 goes to 2 and 4. So I'll add these 2 nodes here. First, put these nodes here actually. So yeah, I'll make this a little bit longer. It's kind of matches, at least somewhat matches this. And then let's see, then 2 has 2 neighbors. So go ahead and I'll add 2 nodes. I'll put the lines in later on. Let's see, 3 has 1 neighbor. 4 has 2 neighbors. 2 nodes here. Come on straight. Keep this up. 5 has only 1 neighbor. 6 has no neighbors, and 7 has no neighbors. A very interesting graph actually, but I guess that's how it is. So the following setups, I think it covers everything. I think it covers all of our cases, I believe. So let's go ahead and just do this. So 1 goes to 2 and 4. So I'll go ahead and put this in sort of in sorted order, I guess. Doesn't only have to be in this order as long as they're both there. We're good. Then 2 goes to 5 and 7. That. 3 only goes to 6. 4 goes to 3 and 6. 5 goes to 7. And maybe I'll go ahead and I'll add one more edge here. You know what? Because this is kind of a very, I'll add 7 goes to 6. I'll put that. So I'll add one more. This was a bit more interesting. And I'll also add one more. Actually, I'll add 4 goes to 7. I'll put that there too, just to make it a bit more interesting of a graph. So maybe I'll say 4 goes to 5. I'll put it there like that. So 4 has 3. I'll go and I'll add one more. It's over here. There, so this way it'll be a bit more interesting of a graph. And so 4 will also go to 5 as well. But it's not in sort of order anymore, but it's okay as long as they're both there. It's a little nicer. That's just fine. And then 7 goes to 6. So I add a note over here as well. So now we'll have a better graph. More interesting graph, I suppose. Okay. There we go. And 6 doesn't go anywhere. Perfect. Okay, so here we go. So you first have to construct this list. So this is going to be really how the computer will see this graph. So as long as we know the neighbors, we can traverse this graph using depth first search. So we're going to first do in main. Of course, we're going to allocate. So actually, I modified this because 7 does go to 6. I modified it, but 6 has a null because 6 has no outgoing neighbors. But I just added one more for 7 just now because otherwise the graph was kind of boring. So 7 goes to 6 in this case, but 6 has a null right there because 6 has no outgoing neighbor. There's no edge coming from 6. So 3, 4, and 7 go to 6, but 6 does not go anywhere. So it's a null. Yep, no problem. So we first constructed our adjacency list using this. This is going to be the graph. This is our visual representation of our graph, but of course, this is going to be what we're going to use to actually traverse the graph. So again, once again, the order in which these node IDs appear does not matter as long as they're all there. So for 4 goes to 3, 4 goes to 6, 4 goes to 5, any order would be just fine. But as long as they're all there like that, we're good. So of course, you would have to allocate. So I'm going to go ahead and just sort of put this here. Just you don't have to really, really actually write this out, but allocate the visited. What other array do we have? I think we have just the predecessor array. So allocate visited, predecessor. I guess also the ADJ list arrays. So we just kind of went over how to allocate this array. Now visited and predecessor are one-dimensional arrays, so really no big deal. Visited equals new bool vertices. Predecessor equals new int, and then in brackets, vertices. So vertices will tell us how many vertices we have in this graph. And we're going to set all elements in visited to false. So using a simple for loop, visited index I equals false. I goes from 0 to I less than vertices. Not too bad. And then set all elements of predecessors to, I guess, -1, but some type of value, some kind of default value that really denotes that we have not really computed any predecessors just yet. So I'm going to actually I'm going to erase this part here so I can actually draw the arrays over here. So I'm going to go ahead and erase this, but of course you can go back in the video and rewatch this part and get that code there. So I erased it. It's not really truly gone because it will wind up on the internet in a sense or on the cloud. So whatever's on the cloud internet never goes away truly ever. So erasing this is not going to really make that code ever go away. It just it's gone for right now only. So anyway, let's go ahead and allocate our 2 other arrays. So I'm going to I'll make this I'll make it blue, I guess. Actually, I'll make it red. I'll do the same thing. I'll go ahead and I'll make another array. Let's first write the lines out here. So you have 8 elements. So be the array brackets. Just copy this. Okay. This is going to be my visited array. This will be my predecessor array. So visited, I'm going to mark all these to be just false. Means you haven't gone anywhere yet. I'll set these to -1 for predecessors. That was a long time just setting up this graph, but setting up this problem. But here we go. We have all of our portions now constructed. So now we're going to have to go ahead and run that first search. So to do this, in main, I'm going to write my for loop. So for int I equals 0, I less than vertices I plus plus. I'm going to just call DFS, pass in I, pass in ADJ list, pass in visited, and pass in predecessors. Guess that'll be it for int main then. So the idea is we have this loop because this graph could be disconnected. So I'll explain afterwards like why we actually did it like this, because there's a chance that from node, so we're starting from, so right now I is 0. So we're going to start this from node 0. That's we're going to start from that node to traverse our graph. So there's a chance that from node 0, not every node can be reached. So you have to potentially call DFS again, have to restart DFS on a different node so you can make sure every node is going to be sort of reached essentially. But that's why that loop exists. But this is first kind of just step by step. So I'll go over what happens here. But we first call DFS and cur is going to be 0 initially. The I is 0. Then we pass in all of our elements in here. So let's write the code now for that first search. So the first thing we'll do is we're going to say, well, if visited, so cur is going to really be the node ID that we're currently on. So we first call DFS, we pass in I, which is 0, into cur. So right now, looking at node 0 at this moment. So if we've already been to this node, then we want to get out of this function right away. If you've already been, this is actually just a precautionary thing. So just in case if you've already been here, we don't want to come back. So if we haven't been to this node, then I'm going to mark it as visited, which means that we've already explored, we've already been to this node before, so there's no need to go back here ever again. And then I'll go ahead and I'll see out cur, which in this sense, I'm going to go ahead and just sort of box this in, as in very similar to what we had with our binary tree traversals pre-order. We could actually do more than just see out the node ID. But for now, let's go ahead and just see out the node ID. But of course, you could do more than that, though. So I'll put that part in green, which means you could do other things to this node if you wanted to, besides just simply outputting the node. But anyway, that's how we have that. And this is going to be our recursive portion, but it's going to be wrapped in a loop. So for node star I equals ADJ list, index cur, I not equal to null, I equals I arrow link. So this loop is going to traverse to all of cur's neighbors. So cur is 0. An ADJ list index 0 is going to retrieve this pointer, this 3 node right here, this node right over here. It returns that node's address, and actually I should have said IT. I'm going to use IT instead. So IT for, I guess, for iterator. I'll use IT instead of I. I'm already too late now. So anyway, I is going to point to this node because ADJ list index 0 is going to be this address. And that address will be assigned to I, which means that it's going to point I to that first node. And we're going to traverse to all the neighbors of ADJ list cur, or in this case, 0. I'll go over that more formally in a second. You first check and see, well, if not visited I arrow ID. So I arrow ID is going to be a node ID of one of cur's neighbors. So if cur is 0, then I arrow ID will be one of the neighbors of node 0. If that neighbor has not been visited yet, well, then we're going to go ahead and explore that node. I'll first do the following. I'm going to first set a predecessor um, ID equals to cur. So the whole point of doing this is we want to mark the predecessor of I arrow ID. So we're going to a new node. We're exploring. So we want to go ahead and make sure that we store that we came from cur to get to that node I ID. So when I draw this out, will make more sense. Then we'll call DFS and pass in this new node ID, and then pass in the same stuff, pass in the adjacency list, pass in visited, and pass in predecessors. Or is it predecessors or predecessor? Predecessor. Like that. And then at the end, we'll just return. And once again, we could do more than just return. So again, I'll also box this in as well, just to kind of denote that we could do more than this. So think of that first green sort of block as like your pre-order work for a node. And that other green block, maybe I'll make it a blue, I'll keep it green. This other green block is going to be your post-order type work if you want to do other things after you finish it, after you process the node. But that's really it. Not a very complicated sort of code to do that first search. So anyway, I'm going to, of course, now trace out our code so we can kind of make sense of all of this. And hopefully just tracing out will make more sense than just, I mean, this code is right there, but of course you want to try to make more sense of it than just looking at code. I want to try to understand how this code actually works. So the first thing I'll do, above, I'm going to put an output section right there. And I'm going to also put my stack. So basically this uses a stack because recursion happens. So recursion, of course, is going to have a system stack in the background. Every time you push, we call a function, it will push onto the stack. Returning from a function will pop off the stack. I guess in 326 you learn about that in more detail about, activation records and so forth. So in our main, we first allocate all of our arrays, which, we did right there. So everything is all set up. These elements in red are going to be our structures we have to maintain. So in our main, we have I equals 0. So we call DFS and pass in 0 into this function. And also we pass in our 3 arrays. So in our stack, we first just call DFS 0. Now, we also pass other things in as well, but I want to focus mostly on just the ID, because that's the only really important part, I guess, at least in terms of understanding this traversal. So we call DFS, pass 0 in for cur, and you've also passed those 3 other elements. Okay, so let's run this code. We first check. So if visited cur, which cur would be 0 in this case because we passed in 0 as the cur initially. So visited 0 is actually false. So we're going to escape this if. The first thing we'll do is we're going to mark this node as true, as visited this node. Okay, so I'm going to mark it as true. Actually, I'm also going to maybe also do the following as well. I'm going to put these markers on our nodes to help us kind of see. So I guess the white markers mean that we have not visited this node yet. And now I'm going to put blue here to mark that. Oops. That I'm going to mark it with blue, indicating that we have seen this node. Okay. So first thing we do is after we skip the if statement, return, we're going to just set this to true, which means that from now on, we're always going to know we've been to node 0. So we don't want to go back to 0 if there's another path that goes back to 0. So now what we're going to do is we're going to output cur, and cur in this function instance will be 0. So we output 0. That's the ID. That's the node we're currently processing. And then we're going to run this loop. We're going to set I equal to adjlist index cur index 0. So we're going to have I point to the head node of adjlist 0. So adjlist 0 is going to be this node. That front node, because adjlist 0, that's going to contain the address of that head node of that linked list. So I will point to this node right there. Okay, so you have to go ahead and explore all of node 0, node cur's neighbors. So I is a pointer that points to a node, so I arrow ID is going to be 3. So then check, have we seen 3 yet? After we look at a node, we check if we've seen this node. So I arrow ID, which will be 3 in this case, so not visited 3. So index 3 contains false, so we have not seen 3. So we're going to go ahead and we're going to explore 3. We're going to first do the following. We're going to set predecessor I arrow ID. So predecessor 3 equals 0, because cur is 0 in this function body. I arrow ID will be 3, so predecessor 3 equals 0. What that tells us is that we came from 0 to get to 3. So 3's predecessor is 0. That's how you read this array. So 3's predecessor will be 0. Okay, so we're going to have to pause this function, and now we're going to call DFS and pass 3. Okay, so we're going to call DFS and pass 3. Okay, sure. Because we can see here that we call DFS and we pass in I arrow ID. Well, in that right there, I points to this node 3, so I arrow ID is going to be 3. So we'll pass 3 into our DFS, and also going to pass in the same stuff, our agency list, our visited array, and our predecessor array. Those 3 are going to pass every time. So we're going to focus mostly on just the IDs, because every DFS call passes in those 3 arrays. So we're going to focus mostly in this picture, focus only on the current number, current ID that we're on, because that's only really interesting part. So I put this in. So first, now we call DFS3. Okay, fine. So now cur in this function body will be 3. So we check. So if visited cur, or if visited 3, let's check 3. So 3 is marked false in our visited array. We're going to skip this return, and we're going to now mark it as now we've seen, we've explored, we just arrived at node 3. So visited cur or visited 3, because cur in this function body will contain 3. We're going to mark it as visited. I'll also mark it here in this picture, so I'll put a blue marker telling us that we've seen this, basically. So now what's going to happen, now I'll also do the file, also put this here as well. So in green, this is going to be our predecessor. I'll put this here as well. That means that we came from 0 to get to, oops, going to 3, my mistake. My mistake. And this green arrow going back is going to just denote that that's the predecessor. So we came from 0 to get to 3. So that green arrow was not part of our graph. I'm just putting that there just so we can help us visualize that. That's what predecessor really stores. So that means we came from 0 to get to 3. So anyway, actually maybe I'll just mark, maybe I'll do like this. Actually, it's probably more natural. So I'll do like this. Just mark the edges that are part of my depth first traversal. Okay, that's probably better actually. So now we're going to mark 3 as visited, and we're going to output 3 to the screen, just because, like that. I should have actually, this should be blue actually. That's wrong to say. Okay, so now we're going to traverse all of 3's neighbors, because right now in this function body we have this loop. So node star I equals adjlist cur. Cur is going to be 3 in this case. So I will equal adjlist 3. So we're going to create another I variable. I'll put it out here because I'm out of space, but I have enough space to at least draw this again. That. So this I is a different I local variable in different function bodies. So these two i's are both local variables in their own function, so they're not related to each other. But this I will, what am I doing here? It's supposed to be 3. Okay. Try this again. There we go. So anyway, I will point to that first node in this list. You first check. So remember in our code, we actually say if I arrow ID is not visited. Well, I arrow ID will be 6, and we check. So 6 is not visited. So we're going to explore node 6. So we're going to first, so let me just go back to our code for a second. We check. So not visited, I arrow ID. So not visited 6, because I arrow ID would be 6 in this case. It's not visited, so we're going to mark it as a predecessor. So we're going to set predecessor 6 equal 3. We came from 3 to get to 6. So we're going to go over here, mark this as 3. I'll put a green arrow here just to denote that we got the 6 from node 3, just as a marker. So a green arrow is not part of our graph. It just helps us denote which path we took to get to 6. Then we have to go ahead, and next we're going to call DFS and pass an I arrow ID, or pass in 6 into this. We're going to pass 6 into this function call, and we're going to pass in the same 3 elements again. So we go ahead and we call DFS, and we pass in 6. Okay, so we call a new instance of DFS, and cur in this function body is going to contain the value 6. Okay, so if visited 6, well, 6 has a false in the visited array, so we're going to skip that if statement. We're going to set visited 6 equal to true. So that means now from this point on, we've seen 6 before. We explored this node, so you don't want to go back here again. So I'm going to now mark this as blue as you visited this. And now we're going to output 6. And then we're going to basically have this for loop. So we're going to set I equal to ADJ list index cur index 6, because cur in this function instance would contain 6. So we're going to set I to point to that first node, and well, it points to null. So that's it. We're done with this because that loop is now done because I equals null. So this loop will escape immediately and return. So we hit a dead end. We couldn't go anywhere because from 6 there was no neighbors to go to, so we're done with that. So we're going to back up to the previous elements. We're going to using a green arrow, just so use red to denote that we're going to back up. So we're going to back up to the previous node. So looking at our stack, we know the last function call we had was we called DFS3. So you back up to the previous node. So in this case, you back up to 3 because that was where we came from. So the stack, this stack is actually going to be at the top. It's going to be the bottom actually, and then the top will be at. So the bottom of this list is our stack top essentially. We're pushing in that order, I guess. So the top is going to be 6. We popped our top element. Our next top is going to be DFS3. So looking at DFS3, we last left off in DFS3 right here in this for loop. So we called DFS, we passed in 6, remember? So now we're going to have to go back to our loop, increment I to the next element in our list. So I, after 6, well, I is going to contain null, because after 6, the next element is, in fact, going to be null. So we're done with this loop. So we're going to escape, and we're going to pop off the system stack. So we go back to 0. So looking at a more pictorial representation, We started from 0. We picked an edge to 3. From 3 went to 6. From 6 we couldn't go anywhere, so we went back to 3. And then from 3, well, we have no other neighbor, so you go back to 0. So that was the way to see it. 0 went to 3, 3 went to 6. 6 had nowhere to go. We backed up to 3. From 3, there was nowhere else to go. We already tried that edge from 3 to 6. There was no other neighbors, so back up to 0. So now we go back all the way back to 0. So when we call DFS 0, we last left off in this loop. We called DFS and passed in 3 into that function body. So now we're going to have to jump back to our loop and increment I to our next element in our linked list, which is going to now move this I pointer over to the next element. And we're going to check, have we explored 1? Because I arrow ID is going to contain 1 in this case. Have we been to 1 before? So we're going to first check that in our if statement. And we can definitely see that I arrow ID, or 1, index 1 of our visited array contains false, so we have not explored 1 yet. So let's go ahead and explore 1. So we're going to have to first set the predecessor I arrow ID to predecessor 1 equals 0, because cur is 0 in this case. I arrow ID would be 1, so predecessor 1 equals 0. So that way we're going to mark the predecessor. So 1's predecessor is 0. Also put a arrow over here as well to help us denote that we came from 0 to get to 1. So, but the predecessor array is going to be used to construct the path, but we'll go over that towards the end. So anyway, now we're going to go to node 1 because we first set the predecessor. Then we call DFS and pass an I arrow ID, or in this case, I arrow ID is going to be 1. So you pass 1 into DFS. So we're going to call DFS again, but pass 1. Kind of branch off. We have a different sort of, so we're going to push DFS on top of our stack. I want to draw it like this so you can kind of see the paths that we took for our, for our DFS traversal. So we call DFS 1. We arrived at 1. And then if you look at our code, the first thing we do, cur would be 1 in this case. We first check if visited 1, which in this case, visited 1 would be false. We skip that if statement, and we're going to set visited 1 equal to true, marking it that now we've seen 1. I also mark it here as well, that we've seen 1 before. Okay, and then we're going to have to run this loop next. I'll probably just go back. I'm not going to bounce back and forth my code. I'm just going to stick to this picture from now on. So hopefully you have the code written down. You can take a screenshot of it right here if you want. I'm going to stay at that picture from now on to make this go a little faster. So take a screenshot, take a picture of this code right here so you can kind of follow along with me. So I think I kept it there long enough where you can have a screenshot taken or whatnot. Haven't copied it down yet. So what's going to happen now is we have our loop. So currently we're on DFS 1 and we're going to look at all of 1's neighbors. So we're going to create I pointer and I will set to ADJ list index 1. So this I pointer is going to point to this node. So we're going to first check. So have we seen 2 yet? So if statement checks to see if not visited I arrow ID, which I arrow ID contains 2. And we see that 2 has not been visited yet. So we're going to now explore 2. So we're going to set the predecessor. So basically 2's predecessor, we're going to set it equal to 1. Remember in that code, in that code, remember we say predecessor I arrow ID equals cur. Well, I arrow ID is going to be 2. Cur is going to be 1. So 2's predecessor is 1. So we came from 1 to get to node 2. So now we're going to go ahead and call DFS and pass in 2. We're passing an I arrow ID into DFS function call. So we're going to go ahead and call DFS and pass in 2. Like that. Okay. Looking at DFS 2, we're going to first check. Okay, so you first in our code for DFS, you first check and see if visited occur. So visited to does contain false. So we're going to skip that if statement, and we're going to basically mark this as visited. So visited cur or visited to, because we're passing in two into that function body. So in that function body, cur will be 2. So we set this to true, marking we've already been to this node. And now we're going to go through all of 2's neighbors. So in our loop, we're going to set I equal to adj list index cur or adj list index 2. So this I pointer in that function body will be set to this node that contains 5. So I arrow ID is going to be 5. We're going to first check, have you been to 5 yet? Well, visited at index 5 contains false, so we have not been there. So we're going to now set 5's predecessor to be 2. And then we're going out, so I'll go and I'll put this green arrow here just so we can help us denote that that is the path we're taking. And then we're going to call DFS and pass in 5. So we're passing in I arrow ID, which is the neighbor of 2. So we enter 5, so cur in this function body will contain 5. We first check visited 5. It contains false, so we skip that if statement. Then we're going to assign visited 5 or visited cur equals to true, marking that now we've been to node 5, so we don't want to go back here ever again. We're going to mark it as now visited. Right there. Then we're going to have our loop, which will traverse, we'll look at every neighbor of 5. So we're going to go to index 5 of our adjacency list and create an I pointer that points to that node. Okay, so now what's going to happen is we're going to say, well, we check and see I arrow ID contains 7. Have you been to 7 yet? Well, index 7 of visited contains false. We have not been to 7 yet, so we're going to explore 7. So we're going to now do the following. We're going to just mark 7. 7's predecessor is going to be 5. Remember, we have that predecessor array at index I arrow IDs, index 7, equals cur. And cur in this case is going to be 5 because we just called DFS on node 5. So we have the predecessor of 7, which will be 5. I'll draw the green arrow here so we know the path that DFS took. And then what's going to happen is we're going to now go to node 7. So we're going to call DFS and pass in 7. So what's going to happen now is we're going to call DFS and pass 7. That's the neighbor of 5. Like that. And what's going to happen is, well, we're going to enter this function body. We're going to call we have 7. 7 will be our cur in this instance. We first check visited index cur or index 7. It does contain false. We skip that return. And we're going to then mark visited cur or visited 7 to be true, which means that we've now seen 7. Didn't actually output over here. My mistake. Okay, so fine. Let's do 0, 3, 6, and 1, 2, 5, 7. I apologize. I guess the output was not the most important part anyway, but the first output 0, then 3, then 6. We backed up. Output 1, 2, 5, 7. Okay, I'm sorry about that, but I guess it's not the real main issue, I guess, anyway, so that's fine. So output 7 next. And then we're going to basically now, looking at node 7, we mark it visited, and we're going to explore all of 7's neighbors. So we create that pointer, I, which is going to just point to that first node, because remember we set I equal to adj list index cur, and cur will be 7 in this case. So I will point to that node. Then we check. So I arrow ID is 6. You first check in that loop if not visited I arrow ID. So if we have not seen 6 before. But we can see here in our array, this contains true, which means you've already seen 6. So we're not going to take that edge. we're not going to explore that edge because we've already seen 6. So we're going to, the if statement will not allow us to call it. So we're going to now set I to the next element, because looking at our code, first, after looking at, so I points to a node. So IRYD, which was 6, so not visited 6 actually was false. So it's going to escape out of this if, and it will try next pointer. So it's not going to call DFS on IRYD if you've already seen that node. In this case, you've already seen that node, so we're going to not call DFS, but instead move I to the next neighbor. Next neighbor is going to now be null. There's no more neighbors after 6, which means that, well, that loop will stop, and we're going to escape function 7. We're going to pop the system stack and go back to the previous function call, which was DFS5. DFS5 last left off, we called DFS and called DFS on I arrow ID or called DFS7. So now in our loop, we have to go to the next element. So for 5, the next element after this node would be null. This function also stops. So we're done. So we're going to now return. I'm going to return from this node 5 and go back to node 2. Back up to node 2. So in node 2, we called DFS on 2. We basically last left off where we called DFS on node 5, which is one of the two's neighbors, which was I arrow ID. So in our for loop, we're going to have to try the other neighbor of 2. Other neighbor of 2 is going to be 7. So we're going to see, well, let's go ahead and first check, have you seen 7? So I arrow ID contains 7, and visited 7 contains true, which means it's already been there, so we're not going to call DFS on that node. The if statement at the very top of our for loop, this is going to make sure we don't call DFS if you've already seen that node. So now what happens is, well, after we look at 7, okay, fine, we have to try next neighbors. So that loop will just one by one call DFS on each neighbor one at a time, or not call it, depending on if you've seen it before. In this case, after we look at 7, okay, fine, next node would be a null. So now we're done. We looked at 5 and 7, it's a null, so now we can escape that for loop, and we can jump out of this function. Return means to escape this function. DFS2, so go back to DFS1 to back up. So remember, what happened here was we looked at 2, then 5, then 7. 7 had nowhere to go, we backed up to 5. From 5, we had nowhere else to go, backed up to 2. From 2, nowhere else to go, we back up to 1. That's kind of what we do. So DFS, all it does is we just pick an edge. A dead end is reached, we back up to the previous element and try a different path. That's all we're doing. And so far, from 5, there was no other path, and from 2, there's another path. We had another path actually, but we've already seen 7 earlier, so we don't have to take that sort of path. So going back to 1. So we go back to DFS 1 and we check. So from 1, we last called DFS and passed in 2. So now we're going to have to run that loop and go to the next iteration of our loop, which will now be set this I pointer to our next node in my linked list. Right there, the 4. We first check 4. So 4 is actually not visited because visited I arrow ID, which is going to be 4 in this case, is a false. So we actually can explore 4. The first thing we'll do is we're going to mark 4's predecessor to be 1. We're going to put a green arrow here just to denote that that's the path we take. And we're going to call DFS and pass in 4. Looking at 4, we can see that 4 is not visited. So we're going to mark it visited. I'm going to go ahead and output 4 this time. It's actually not the most important part really, but the output, I should have output earlier, my mistake on that. And now from 4, we're going to have our for loop, which will set I to point to ADJ list index 4. So I will actually point to this node right there. We check. So I arrow ID contains 3, which 3 has been visited already because we can see index 3 in this array contains true. So we're not going to call DFS on that node. So okay, fine. Try the other neighbor of 4. So 6. Let's look at 6. It's visited. Index 6 is actually true. So okay, fine. Try next element. So ID is going to be 5. So DFS 5 is also marked true. So okay, fine. Try next element. Which will now be null. And that's it. Our loop is now done. So now we're going to escape out of this function. Go back to DFS1. In DFS1, we last left off, we called DFS and passed in 4. Last left off right there. So now we're going to have I move to the next element in our linked list, which will be null. So that means we're done with node 1 as well. To return back up to DFS0. DFS0, we last left off on that right here. We last left off right there. So we're going to resume from that spot, which is going to be simply move I over to the next element. So after 1, next element is going to be null. So that function is also done. So we're going to break out of here. We're going back to main. So back in main, after we finish DFS0, we jump back to main, and we're going to now call DFS1. DFS1 returns back immediately because visited cur actually contains true. So we would call DFS1, DFS2, 3, 4, 5, 6, and 7. Each returns back immediately. So you're wondering, well, why do we actually have a loop? Because if I just pass in just 0 by itself, it went through every single node. So why do a loop? Well, it's if in case from node 0, if there are some nodes that cannot be reached from 0, we would go ahead and restart DFS on a different node to make sure every node is going to be visited. We want to be able to touch every single node basically. So if let's say there's certain nodes you can't reach from 0, restart DFS on that node and then continue DFS so you can reach every single node. But anyway, that's going to be our DFS traversal. And those green arrows right there denote our paths, essentially. To get from 0 to 6, we went from 0 to 3, 3 to 6. To get to, let's see here, from 0 to 2, we went from 0 to 1, 1 to 2, and so forth. So we can kind of see this sort of path, I guess. We can see this structure. So, okay, that's our traversal type. I guess let's go over how do we actually use this predecessor array to construct the paths. Because right here, looking at the picture, we can follow the green arrows and find our paths. But of course, the computer, though, is going to use a predecessor array to actually do this. So, okay, let's go ahead and sort of do the following. I want to find the path to get to, let's say, 5. So output a path to 5. So what we do, I'm not going to write the code for it, so I'll go over just to kind of give you an idea of how this code would look like. So we're going to have a stack. And what we're going to do is first we're going to push 5 onto our stack. And then looking at predecessor 5, that contains 2. So we're going to push 2 onto my stack. Going to node 2. Node 2, so 2's predecessor is going to be 1. So push 1 onto my stack. And then 1's predecessor is going to be 0. So push 0 onto my stack. And then 0's predecessor is, I guess, -1, which means that 0 has no predecessor. So that's it. So this stack from top to bottom, this will give us our path. So 0 to 1, 1 to 2, 2 to 5. So this predecessor array is a very nice way to maintain. This is how we can construct our path. We construct it in reverse order, but it's okay because the stack will reverse that reverse order, which is going to be in the right order. So we can see from the green arrows, we have 0 goes to 1, 1 goes to 2, 2 goes to 5. That was the actual path that this DFS constructed from 0 to 5. So I also can do other paths as well, but really all I have to do is take the, I want to find a path to any node, push it onto the stack, and then just go to that index, take that predecessor value, push it onto the stack, and keep doing this until eventually we hit a index that has no predecessor, that we're done. And the stack from top to bottom will give us our path, essentially. So if you want to construct the path as well, that's how you would actually do it using this system, using this custom stack we create. We can construct our path like this. So we construct it in reverse order, the stack will reverse that reverse order, which will put it in that right order. So, okay, so I guess a DFS is used mostly to do a traversal. It can be used for a search. It can do other things. It can also update elements in our graph. It can update the nodes. It can also construct different paths that we created. So one question is, okay, does DFS guarantee the best possible path? Let's write some notes down over here so we can look at this. So here's some notes on DFS. So does DFS guarantee the shortest path? So in this case, shortest path really means the path with the least number of edges. Well, let's go ahead and take a look. So right here, we found a path, let's say from 0 to 3, which is the best path. Let's look at 0 to 7. What is the best path from 0 to 7? Well, I think 0 to 1, 1 to 2, and then 2 to 7 is actually a better path. But in our example for DFS, the path that it found was 0 to 1, 1 to 2, 2 to 5, 5 to 7, which is also a path, but it was not the best path. A better path would have been 0 to 1, 1 to 2, 2 to 7. But our depth first search did not actually find that path. So the answer is that, well, not for sure. So I'll write this here in red. Does not guarantee the shortest path. I mean, it doesn't guarantee it. It might find a best path. So you can't say it will never find the best path. It could, but it's not going to guarantee the best path. DFS is not designed for DFS is a very simple traversal, which can be used for different applications of graph theory, but it's just designed as a very basic traversal through a graph. Not for sure. So, I mean, we can have a weighted sort of graph, but for unweighted graph, we can think of every single edge having a weight of 1. So we can find shortest path for unweighted, just assume that every edge has a weight of 1, which that essentially would be technically unweighted because every edge has the same weight, basically. So a different traversal type will have to be used actually to find the best possible path, which we'll cover next week. So anyway, another topic on depth first search is that if a path does exist, it will find it. So there's another sort of bullet here. If a path from X to Y exists, DFS will find a path. Maybe it's not going to be the path, but it will find a path for sure. And it's because the order in which we have our elements in our adjacency list determines what path it will take. So over here, for example, from 0, I chose 3 first because our list contains 3, then 1. I could have had a 1 first, then 3. So the order in which you have these nodes is going to determine the traversal DFS will take. But I mean, because of that order being different, it's going to give a different sort of path, but it's okay. If you only care if a path exists between two nodes, well, DFS will find it. So we can sort of do that. So DFS is mostly used not for the best path, it's used for different various, I'll go over examples next week on different graph theory sort of algorithms you can use. And DFS is a very nice algorithm that covers or that can perform different sort of tasks. Like for example, finding a cycle in the graph is one use of a DFS. Topologically sorting a graph, which I'll definitely cover that because we have a very interesting example we can use with topological sort. And also, yeah, so DFS is a very nice, simple traversal which can be used for various different graph problems. So let's not go over the runtime analysis, and then we'll be done with this. So I might take a little more time past 9:45, but it's okay. I won't take too much more time. We're almost done. So I guess it's very simple to analyze the runtime for depth first search. So each edge is looked at once. Let's go back to the to our data structures here. You notice this we had several loops for every function. Each loop traversed all these nodes. So if you look at them, every single pointer I eventually equaled null in each function call. So we basically had to go through every single node in this structure. Each node represents an edge because you have 0 to 3, 0 to 1, 1 to 2, 1 to 4, and so forth. So every single node represents an edge. So every edge gets looked at once, no more, no less. Every edge looked at exactly once. Now, there are moments, let's say, for example, like for example, 2 to 7. This edge is not part of our depth first search traversal, but in order to know that 2, so let's say, for example, I want to check if 2 goes to 7. I want to see if, actually, so we went from 2 to 5, 5 to 7. Then we tried 2 to 7, and we found out that, oh, well, we've already been to 7, so don't take this path. But we had to look at this edge in order to know that 7 has already been visited. So every edge is looked at. Either we take that edge and explore that neighbor, or we don't explore that neighbor. But either way, though, we had to look at this edge, one way or the other. So every edge looked at once. So the runtime is going to be really O of E, or the cardinality of E. Very nice linear runtime. So if you have 10 edges, it'll take 10 steps. If you have 20 edges, 20 steps. Now, also in Wikipedia, you might see the following sometimes as E plus V like this, because they're trying to be very nitpicky, because if it's a sparse graph, it's O of V, the dense graph is O of E. But either way, though, it doesn't really matter because the amount of edges you have really determines the runtime. So that's kind of overkill. So really, O of E is actually just good enough. So that's a runtime for depth first search. A very nice, fast algorithm because it's linear with respect to the number of edges. So pretty good. So anyway, that'll be it for today. So I guess take care, guys. Thanks for watching. Stay safe. Have an awesome weekend. And I will see you guys next week.